Hi everyone, my name is Emily Wade and I'm here with Ashley Russell. I'm one of the engineering chicks, and today we're going to be going over some simulation and finance information. So the first topic we're going to talk about is Brownian motion. And so in Brownian motion, you have a continuous state and continuous time stochastic process. And so the process has independent increments, and that means that if u and v and t and s are non-overlapping intervals, then b of v minus b of u and b of t minus b of s are independently distributed. And so then we have the standard Brownian motion follows this formulation right here. And so this process may be simulated in an interval such as 0, t, and by dividing it into a large number of n subintervals, each of the length h, so that t equals n times h. So that's how you get t in this interval. So the next thing we're going to talk about is asset price movements. And so this is used if we want to model the price movements over time of an asset such as a share or interest rate or commodity. And so this follows the geometric Brownian motion, and you've got a couple of variables that you're going to need. You need mu, which is growth rate, sigma, which is volatility, S, which is initial stock price, R, which is your random normal variate, and T, which is your time period. And with this, each realization shows how the price of an asset subject to the geometric Brownian motion changes over the given time period, T. So the next thing that we're going to talk about with simulating and finances is going to be the pricing, simple derivatives, and options. So in this context, a derivative is a contract that depends in some way on the price of one or more underlying assets. And then an option is a derivative where the two parties have certain rights, which they are not obliged to enforce. So the simplest type of options are European call and put options, which we're going to talk about in the next couple of slides. But the Black-Scholes differential equation models the change in portfolio value over time. And as you can see, that's this equation right here is the Black-Scholes differential equation model. And this is advantageous because it doesn't contain mu, the expected growth rate, since it's unknown. And fun fact, Black and Scholes won a Nobel Prize for this formula that does not contain mu.
Okay, so now we're going to talk about the European call option. So this is a very simple type of option, and normally you don't need to simulate this, but in our book they did it just as an easy example. So the European call option is an option for the right to buy a stock or an index at a certain price on a certain date. And this is different from an American call option that can be exercised at any point by a certain date. So there's a little bit of difference in the wording there, but that does end up making a big difference. So with the European call option, you're only concerned with the price of the stock or index at its expiration date. So here we found a source that summed this up pretty nicely. It says that the European style options tend to be cheaper than American style options because if a stock spikes prior to expiration, an American style call option trader can capitalize on that increase in value, whereas a European style call trader has to hope that the price spike holds until expiration. So now we have the European put option. A put option is the right to sell shares of a stock at a certain price, called the strike price, before the expiration date of the option. So a put option has 4 characteristics. First, there's an underlying stock or index to which the option relates. Second, it has an expiration date. Third, it has a strike price. And fourth, the put option is the right to sell the underlying stock at the strike price. So this is different from a call option, where the call option is the right to buy stock at the strike price. The put option is the right to sell it at that price. Okay, so now we're going to talk a little bit about continuous income and how that affects the formulas that we've been using. So formulas for the previously discussed concepts are changed when the underlying asset earns a continuous known income at rate R sub f. So previously the Black-Scholes differential equation was this right here, and then now with continuous income it becomes this here. So this is all the same on this side of the equation, but right here there's a difference where you include our, it looks a little bit different when you have this continuous income. So finally, we're going to talk about delta hedging. Delta hedging is an option strategy that tries to reduce or hedge the risk associated with price changes in the underlying asset by offsetting long and short positions. So for example, a long call position may be delta hedged by shorting the underlying stock. So based on the change in price of the option caused by a change in price of the underlying security. And then we found another source that was helpful here. An options position could be hedged with options with a delta that is opposite to that of the current options position to maintain a delta neutral position. So this just kind of basically is saying it helps you offset the risk. And so here are the sources that we use. Feel free to check out any of them. They're all really great sources, and they go way more into detail than we were able to go into in this video. That's all we have for today. Thanks for watching.